Welcome back, everybody. So I hope everyone saw my email on Friday just to clarify everything that was going on with it. So originally we were scheduled to take exam one on Wednesday of this week, but since that would mean going over 1.5, all of it today, and then and fully digesting it in a day and a half. That seemed a little bit too difficult for short-sighted by my opinion. So I've decided to move exam one to the 22nd and then move quiz three to here. So we're still so we don't have to for a myriad of reasons, one, to practice more in the upcoming exam. And then additionally, that way we don't have to have exam followed by a quiz immediately. Yes.
Is quiz three just gonna be over unit one though, not?
Yeah, it'll be over 1.4 and 1.5. So, Alex, yes.
So that means today is just 1.5 or also 2.1?
If we get a chance to, we'll go to 2.1, but I am skeptical. I'm skeptical. Okay. So that's right. That's right. That means it's going to be a very fun chapter. So once again, the whole rule that we learned where you can ignore, first and foremost, that when it comes to limits at infinity, when you go to infinity, positive or negative infinity, you can just start ignoring all the lower degree terms. So we saw that in 1.4.15, A and B. You can immediately get rid of so in part A, you can immediately get rid of the minus 5z cubed plus 9, and then the plus 12 in the denominator, and then reduce that, cancel some stuff out and see what happens. So 29c squared, as z goes to negative infinity, that would be positive infinity, because it's going to be negative infinity squared, if, quote unquote, and anything negative squared becomes positive. So Uh, hopefully you guys were able to figure these ones out. It's just taking the limit as x approaches positive or negative infinity to see what happens. JT.
Sorry, for the one we were just looking at, I
Uh,
totally remember. Is it that we're like only taking the first like 2z6 and 9z4?
Mhm.
We only taking those because it's negative infinity, or like if it would have been 2z squared and it was like a factorable problem, would we like factor it, or how do we know this?
So
Just take the front ones.
it's because we're going to infinity. Like that we just look at the highest degree terms. That is the only time we would do that. Because that's remember, in limits at infinity, that's talking about the end behavior of the function that's inside the limit.
Okay.
So,
If
mhm,
it was like limit z to like -3,
mhm.
then you wouldn't do this.
Yes, yeah, yes, that's correct. This only works when you're dealing with limits at infinity, because we're talking about end behavior then. So then we learned real quick that you can bring the limit on the inside of a radical, so long as it's defined, as we'll see in the next example here, with the added caveat that the even powers of the even roots of something to the same even power ends up being absolute value. So if you have the fourth root of x to the fourth, that is the same thing as the absolute value of x. If you have the 16th root of x to the 16th, that will become absolute value of x. And so with this first one, when we're taking the limit as x approaches positive infinity, once again, we were able to just ignore everything else. That plus 2 doesn't mean diddly squat in the face of infinity. It really doesn't. So we can just ignore it, and then the square root of x squared becomes the absolute value of x. But because we're approaching positive infinity, this is just going to be positive x, because the absolute value symbol would be redundant there, because we're just dealing with positive numbers. And the absolute value of 5 is 5. Absolute value of 100 is 100. We don't need to worry about tacking on an extra minus sign to counteract the negative. So it just becomes 2, whereas in the other situation, when we approach it from negative infinity, now our x values are going to be negative. So in order to counteract that, we tack in order to drop the absolute value inequality and counteract the fact that they're negative, we add on an extra negative sign. The reason we're doing this is because we cannot cancel the x's at their current stage, because they're not the same. If they were the same factor, they'd be able to cancel, but they're not right now. One is an x and one is an absolute value of x. So once we realize that we are approaching negative infinity, we can rewrite it as negative x because now the negative negative will cancel itself out.
If there wasn't the 2 on that one, would it be -1 or negative infinity?
It would be -1. Then we did this one. So as z approached positive infinity, same idea, but instead now we have a fraction. We don't have like a nice number, but that's okay. Z to the 9/4 over z, like z to the 4th root of z to the 9th. That's the same thing as powers above, roots below. So it's z to the 9/4 divided by z squared, which will reduce to z to the 1/4. And that does go to infinity very slowly, but it does. Now the last one, I'm going to say immediately that a D and E. And I want you to try and convince yourself as to why. Take a second, convince yourself why the answer should be a D and E right from the get-go. Okay, so hopefully we had a chance to think about it. Does anybody realize what's going to happen? Keep in mind, the z is approaching negative infinity. What will z to the 9th approach if you approach negative infinity? Negative infinity as well. So as z goes to negative infinity, so I'm going to highlight that. As z goes to negative infinity, z to the 9th plus z plus 2 will also approach negative infinity as well. So the 4th root of z to the 9th plus z plus 2 will not exist. For like up until z equals -1, it will exist, but after that point, it's done. After that point, z to the 9th just blows up to an uncomfortable degree, and it will never ever be it'll never be positive again. So that's why I can immediately claim this one as D and E. So you do have to be careful, especially when you're working with roots, specifically even roots. Odd roots are all chill. They can handle anything. But even roots, they don't like dealing with negative numbers. Okay, any questions on those? All right, some interesting cases. Find the limit as x approaches positive infinity of 2x minus the square root of 4x squared plus 1. So we're going to quote unquote try positive infinity. Because, right, we can't plug in infinity, right? That's impossible. Infinity is a concept, it's not a number. But if we were able to plug in infinity, like looking at incredibly large powers, like values of x, 2x will go off to infinity. Square root of 4x squared plus 1 will also go off to infinity. So we will get, quote unquote, infinity minus infinity. And this is another example of something that we call indeterminate. Right? We already kind of went over this kind of concept last time, or recently, about indeterminate. 0 over 0 is indeterminate because depending on how you look at it, which limits you're using, or what problem you're examining, it could be a myriad of values. It could be 1, it could be 1/2, it could be -7. It is indeterminate to know unless you know more about the problem. And the same thing is true here. We've got infinity minus infinity. There's no way to know which one's growing larger. Are they growing at the same rate? Is it infinity minus the exact same infinity? Is one larger than the other? It's all hard to tell. So we have to do some analysis. We need to do some algebra. What should we do? What should we do? Yes.
Cancel the square root.
How will we do that? JT said it. He stole your thunder. So tell him he's a jerk. Right now, look at him in the face and tell him he's a jerk. I'm kidding. I'm kidding. You guys are correct. We need to take care of the square root, and the only way to do that, we can't square it, right? That's not allowed. That would change the entire expression. But what we can do is we can cleverly multiply by 1. So if we treat this as over 1 and we multiply by the conjugate, 2 plus 2x plus the square root of 4x squared plus 1 divided by 2x plus the square root of 4x plus 1, 4x squared, excuse me. That would allow us to take care of the radical, at least in the numerator. Now, yes, we have a radical in the denominator, but now notice the good thing about that is that now this is 2x plus the square root of 4x squared plus infinity. It's no longer infinity minus infinity. At worst, it's infinity plus infinity, which is infinity. So we have taken care of the fact that we're dealing with infinity minus infinity, and we'll see what happens now. So this will FOIL to, if you take care of the numerator, so limit as x approaches positive infinity, the whole point of multiplying by conjugates is that it makes the square, like it becomes the first thing squared minus the second thing squared. So it becomes 2x squared, 2x quantity squared, that is, minus the square root of 4x squared plus 1 squared, all divided by 2x plus the square root of 4x squared plus 1. Then, luckily for us, that means that the square root and the square cancel. We've got the limit as x approaches positive infinity of 4x squared minus the quantity 4x squared plus 1, all divided by 2x plus the square root of 4x squared plus 1. Any questions so far? Any of the algebra that we've done? And those questions also, please remember with regards to the questions, it might not just need to be like, how did that work? You can also ask things like, how did I know to do that? Those are valid questions to ask. Yes.
If it wouldn't have been like, or if like in the original equation where it's like 4x squared plus 1,
Mhm.
if the plus 1 was outside of the square root, would you still be able to do the conjugate?
So if it had been this,
Yeah, 'cause I just remember one of ours, like the first time we did conjugate, the change in sign was on the like after the square root. So I just didn't know. Like, I didn't realize the 2x minus turned into 2x plus.
no, so it doesn't like it's always this is like if you have something as something minus something, well, let's do plus or minus, then the conjugate would be something minus plus the something else. So the conjugate is always just the same two quantities, but the sign in the middle has changed. So if it starts with a plus, then the conjugate's minus. If this starts with a minus, the conjugate's going to be plus.
Okay.
Yes. Oh no. Okay. So now the 4x squareds will cancel in the numerator, giving us the limit as x approaches positive infinity of -1 over 2x plus the square root of 4x squared plus 1. What would the answer be there for? What is the answer now? Because we can claim the answer at this point. Take a second. Don't say it out loud. You have a chance to reason through it. We're taking the limit as x approaches positive infinity. The numerator is just going to be -1. There's nothing happening there. It's staying fixed. It doesn't increase or decrease. It stays at -1. But the denominator, the 2x, is going to go to infinity. And what about the square root 4x squared plus 1? Is that also going to go to infinity? Yes. So you have this going to infinity and this going to infinity, which means that the whole denominator is going to positive infinity. So what should the answer be? What do you get when you do 1 divided by 100? 0.01. And then 1 divided by 1,000, 0.001. 1 divided by 10,000, 0.0001. And that's just 10,000. We're talking about infinity, incredibly larger. So it's going to be 0. And the intuition, you can write this down if you want, if you need it. We've got a number divided by infinity goes to 0. You take a finite number and you divide it by an impossibly positive or negative number. I can even put plus or minus infinity here. Because 1 divided by negative 100 is negative 0.01. 1 divided by negative 1,000 is negative 0.001. It keeps getting closer and closer to 0, just from a different direction. And then when you finally take the actual limit, it will be 0. Any questions on that? And so, well, I'll wait for a second, because I just want to mention something about this problem. I don't know why there's an A here. There shouldn't be an A. So these all, like, the fact that it becomes 0 as a final answer, we've now just proved it with our mathematics. It makes sense that this infinity minus infinity should be 0, because they're both growing at basically the same rate. Because what would this be? What would square root 4x squared plus 1 be if you just ignored the plus 1? It would be 2 absolute value of x, but we're approaching positive infinity, so it would just be 2x. So you got 2x minus 2x virtually at the end behavior. When we get really, really far out there, it will basically be 0. So that is a cool little nifty fact about that. So there are certain circumstances where that would not be the case. If that was not a 2x, if that was a 3x, then the answer would be 5? I think 5. No, 1. 1. Maybe, yeah, it'd be 1. And then you go further. You can keep messing around with these. Try and do a different one. Try and make it 3x instead of 2x. You'll do the same process, but I guarantee you'll get the same. You'll get another answer that's very similar. And part B is slightly different. This one we don't need to do any work, really, because what's going to happen as x approaches negative infinity? Well, the first piece, 2x, will also approach negative infinity. And the 4x squared, without the minus sign, this will approach positive infinity. So we have negative infinity minus infinity, which gives us our final answer. If we take negative infinity and we subtract off an additional infinity, it becomes negative infinity. Which, once again, seems a little bit strange at first, but it's because infinity is a concept, and it just kind of throws things off. But negative infinity minus infinity, that's just negative infinity. Okay? Any questions on that? All right, we get to the best part, that what we've been all leading up to. Continuity. All I think about is that Rick and Morty episode where it's continuity. If anybody's seen Rick and Morty, it's great. That episode was hilarious. But anyways, continuity. The function f of x is said to be continuous at x equals a if the following 3 conditions are met. Number 1, f of a exists. You cannot be continuous unless your function exists at a value. Your limit, the second point, is that the limit as x approaches a of f of x also exists. But that is not sufficient for continuity. The third and most important one is that the limit as x approaches a of f of x equals f of a. Thinking about it. I've been toying around with this idea, and I might even just decide finally to do it. The original two statements, f of a exists and the limit as x approaches a of f of x exists, those are basically taken care of in the last statement. Because if one of them doesn't exist, then this doesn't make any sense. And if both of them don't exist, then this doesn't make sense as well. So really, all that's required is this statement: the limit as x approaches a of f of x equals x f of a. The limit and the function need to agree at that specific x value. The limit of the function and the function value need to agree at x equals a. That's the key. That's the key. In order for something to be continuous, the limit and the function need to work in tandem. And we'll talk about this definition and how it looks visually in just a moment. If a function is not continuous, meaning that one of those three things has been broken, whether the limit doesn't exist, the function doesn't exist, or the limit and the function don't equal each other. If any of those things break, then we say that it is discontinuous at x equals a. The parentheses meaning like if we all know what we're talking about, we can just say it's discontinuous there, and then we know where there is. But that's what it means to be not continuous, is to be discontinuous. So what it's requiring is that whenever we look at any specific x value, that the limit, so when we approach it from both sides, it always ends up being the same as the function value itself. And this in intuition, from a graphical standpoint, the curve needs, in order for it to be continuous, it needs to be connected. And what I mean by that is you can trace the curve without, is everyone okay with w/out, meaning without lifting pencil from page? You can trace it without ever lifting your pencil from the page. That is the intuition. That's exactly why we use the term continuity. Is like in the broader scheme of things in English, what continuity means is it needs to be consistent. There needs to be no breaks in what you're talking about. If I give a continuous speech, it means I never stop talking. And it just always flows. That's the same thing with a function, just in a graphical format. So here are the four main types that we will encounter. There are more, of course. It's hard to, like, the other ones are a little bit more nuanced that require upper division mathematics. So this one right here. Oh, that's right. I didn't fix this. So we're gonna just add a little tail to that and make that an A. Apologies. Just change those all C's to A's. Oh, and that's supposed to say A. Some textbooks use they use f of c for whatever reason they use x equals c, and other ones use x equals a. I like x equals a more, but either way. So, looking at this curve, what is the issue? There's no point there. So f of a doesn't exist. That's the issue. F of a does not exist. And as a consequence of that, the limit and the function don't equal each other because that's kind of a moot point, right? You can't say that the limit does exist. Yes, the limit does exist, totally fine. But it doesn't equal the function evaluation there because f of a doesn't even exist. So you can't even really talk about condition 3. So, and then with the intuition, if I'm drawing this with my pencil, once I get to here, I have to pick it up from the page and then continue onwards. Yes, if we're drawing, I know there's that whole thing about you can draw a car without ever lifting the pen from the page, that type of thing. Yes, I know you can draw this without whoop. You could do it without ever lifting your pen from the page. Yes, I get you. But that's not what that circle means. That means the function doesn't exist there. We've drawn the circle to imply that it doesn't exist there. So when we're actually, if a graph in calculator is doing this, it's going to stop here, lift its pen from the page, and then graph it again. So the next one. This one, the function exists at a, right? F of a exists. It's whatever this value is. Let's say that's like 5. F of a is 5, but the limit does not exist. Here, the limit as x approaches a of f of x does not exist. Next one is the most nuanced case. It's not continuous. Oh, and going back to the tracing situation here, right? If I draw it, I just draw a little dot, and then I have to lift my pen from the page and then go back again to draw the rest of it. And then the intuition for this one, once again, is I have to draw it. I have to stop, fill in this dot, and then continue onwards. I've lifted my pen from the page or my pencil from the page to draw it. But how do we write that mathematically? Does the function exist at a?
Yeah.
Yes, the function exists. F of a exists. Does the limit exist?
Yeah.
Yes. The limit is whatever this number is. It's like 4 and that's 5. But the problem is that they're not equal to each other. So while f of a and the limit as x approaches a of f of x exist, it's not continuous. Because the limit as x approaches a of f of x does not equal f of a. Yes, Alex.
Hypothetical test question. Say if that was given to us, would we just for an answer have to write the limit of as x approaches a of f of x is not equal to f of a and leave it there?
Excellent question. Excellent question. So if I asked you about continuity, we encountered this on the quiz 2. So when I say explain mathematically, I was a little more lenient this time. I won't be as lenient on exams because remember you do get the redo, which we can talk about in a second. But anyways, if I say explain mathematically, I want you to explain it with math. Words, not good enough. I want math. I want what math properties are being broken or what math properties are being held true here. So if I asked you to verify that this was continuous there, you'd have to say, well, look, f of a exists, the limit as x approaches a, limit as x approaches a of f of x exists, and they're equal. That would be sufficient. If it was not continuous and I wanted you to explain mathematically, you'd have to show me which property is broken. Saying like Well, if you draw it, you have to lift your hand from the page. That's not good enough. That's an intuition. That's not a formal mathematical argument. So yes, that's a good question. So if I say, whenever you see me say justify mathematically, I mean I need to see some math involved, not words. Words are fine if they're going to use the words to describe math, specific math concepts, but intuition does not work. This last one. So f of a exists. And so one student one semester would say, well, we do know the limit does exist. Because the limit as x approaches a of f of x equals positive infinity, right? But does that actually exist? No. We talked about this last time in 1.3. Remember, we say that the limit is positive infinity, but the limit still does not exist. We just know a little bit more about the does not exist situation because there are many different options. If you're talking about the curve sine of x, right? It keeps bouncing back and forth between -1 and 1 as we approach positive infinity. It doesn't converge to a finite value, and it doesn't find some specific thing to go towards. It doesn't increase indefinitely. It doesn't decrease indefinitely. That is a different type of DNE. Positive infinity, that's telling us a little bit more. It says that it doesn't exist, but we know that it grows indefinitely. So the limit at which means the limit as x approaches a of f of x does not exist. We just know more by saying that it is positive or negative infinity. We just know a little bit more. We get to be more technically correct, which is the best type of correct, as we all know. Any questions on those? Okay, so examples A and C, the ones in the first column, those are what we call removable discontinuities. Now, these things, this is just terminology that I might bust out, but I'm not going to ask you any definition questions on this type of thing. So examples A and C are what we call removable discontinuities. Because all I would really need to do in order to make this curve continuous, all I would need to do is just remove that problem. If I remove that, so for the first one, if I just filled in that hole, then it would be gone. I removed the hole, it's a removable discontinuity. Here, if I just cross that out and bring it down, it's been removed. The one problem has been removed. Example B, that is one that is not removable because that would require, if I wanted to fix the issue, I have to bring one entire piece up. Instead of just removing one point, I'd have to completely move another piece to get it back to where it belongs. So this is what we call a jump discontinuity. Because it jumps. Very, very clever, I know. And then example D is what we call an infinite discontinuity. It's a discontinuity that happens because the limit went to infinity. An infinite discontinuity. Once again, I never ask my students questions on verbiage, on definitions. So this is mainly for us to talk about them. Like if I was teaching arithmetic and I was teaching fractions, I'd tell you what the name of the numerator and the denominator. I wouldn't have a question saying what is the formal name of the upper portion of a fraction. I wouldn't do that. And the same thing is true here. It's just that we have more terminology to discuss. All right. So that is continuity in its intuition. Any questions on that? Property. 3 things. Function needs to exist. at the value. So f of a needs to exist. The limit as x approaches a of f of x needs to exist, and they need to be equal. Those are the three things you need. So, got a little bit of a review problem along with some actual continuity questions. Does P of 5 equal 2? No. P of 5 equals 4. Nope. P of 5 equals 4. The limit as x approaches 5 of P of x equals 2. Yes.
So what really matters is the black circle in the graph, because every time I've seen like the other graphs, I've been meaning to ask you this too. There have been like I've seen the white circles and the black circles, so it just kind of confuses me.
Sure. So a black circle means it's an actual point on the curve, whereas an open circle means it's a placeholder. It doesn't actually exist there. So like that's a missing spot of the graph.
Oh,
So that's what that means. It is it's the two-dimensional analog of if I say the interval 1 to 3 like this, here 3 is included in the interval. So every number right before 3 and including 3 is included. Whereas here 1 is not included, but everything up until 1, like everything right above 1 is included. So 1 is kind of like our stopping point. It's not actually part of the set in this interval. It's not part of it, but it's where we stop. So we have to write it even though it's not actually part of it. Does that make sense?
yeah.
So that means that P is not continuous at 5. Then we have the limit as x approaches -4 from the left, which would be 3. That's right. 3. And then the limit as x approaches -infinity is if we keep going up and up and up indefinitely, it goes to positive infinity. Note the limit as x approaches positive infinity of P of x will equal 1. Just as a bonus question. So maybe not note, let's say bonus. Bonus. And on an exam, I would be like if this was a curve that was given on an exam, I would have a little dashed line here to symbolize that it does level off at 1.
So when you're finding that one, you just took whatever part of the line was like farthest to the left. And then look to see which one, like if it would have been pointing down, maybe it said negative infinity.
Yes. So because like this was my first this is unit 1, this is when I first started working with my notes. I was still learning how to mess with Desmos and everything. There should be arrows here and here. There should be an arrow here and there should be an arrow here, symbolizing that as you move to the left further and further out, as our x values go more and more negative toward negative infinity, our y values, our function values, they keep growing up and up and up indefinitely. If it had been like this, like that, then the answer would have been that the limit as x approaches negative infinity is negative infinity.
There would have been like out 1, but it was pointing down, it would still be positive, right?
At vertical asymptote or horizontal asymptote?
Horizontal.
At 1?
Yeah. But like if the arrow was pointing down, it couldn't go through it, right?
It could go through it. So if you had another, like if it was a horizontal asymptote like there, you could have this curve go like that. That's fine. Because there's at least like this would be connected like all the way through. Because there technically is a horizontal asymptote through y equals 1. I denoted it only over here because just to not muddy up the graph. But a horizontal asymptote is a line that goes throughout the entire curve. It's just it only really matters over here. But it is okay for a curve. I mean, this curve could have gone like this. Like it could cross over it infinitely many times as long as like it's just end behavior. It's what's happening way, way, way out there. Okay. And so find the values for where P of x is P is discontinuous. So much like with anything when we're looking at a graph, we should always try and look left to right with our x values because that's the way things work. So and the quickest way to do this is by basically trying to draw it with your pencil. If I'm drawing it, it's continuous over here because I'm continuously able to draw a curved line. Then at -4 is the first time I have a problem because I have to lift my pen up to go down here. So -4 is the first one that we have that's a problem. Then we'll continue onwards. -3.5 is fine, -2, -1 is fine, -1.5. But as soon as I get to 0, I can never reach it. It's an infinite discontinuity because I have to lift my pen from the paper and then go back to 0 right here. So 0 is included. Then we get to keep drawing at 0.5, it's fine, it's continuous. But at 2, it's discontinuous because I have to lift my pen from the paper or my pencil from the paper and draw to the right of it afterwards. So 2. And last but not least, it's still fine after 2. At 3, it's continuous. At 4, it's continuous. It's jagged there, but that's not a problem. That has to do with differentiability, but we'll get there. Fine, 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 fine. Up at 5, we have an open circle here, and I have to jump up to get to it. Well, it's not a jump. It's a removable discontinuity. I have to fill in that point and then come back to it. And so 5 is the last one. After 5, it ends up just being a leveled off curve. It just basically becomes almost close enough to a straight line. So those are the ones. Those are the 3. And we can even add the reasonings for those things if you'd like to add it. So this one, the limit as x approaches -4 of p of x does not exist. Actually, yeah. 0, the limit as x approaches 0 of p of x does not exist. You could also claim that the limit and the function do not exist. You could say that the limit as x approaches 0 of p of x doesn't equal p of 0. That's true too, right? It's still true to say that 0 does not equal DNE. That's a true statement. So that is another option that you could say. But the more accurate description would be that the limit does not exist. Then at 2, the problem is that p of 2 does not exist. The limit exists, and it's roughly -1.5, but that's not enough. You need the limit and the function to exist and to be equal to each other. And last but not least, 5 is that the limit as x approaches 5 of p of x does not equal p of 5. Any questions on that? Yes.
So, in the exam, this is like proving it mathematically, right?
Yes, that would be like, so if I asked you to show, like, to explain why they're discontinuous, you would just need to write that. What I've written in red, blue, purple, and green. So if I'm like, usually the way it would work if I was asking about discontinuity, I might ask you to find all the points where you don't need to justify your answer, and then I might ask for a specific one and say like, hey, is the function discontinuous here or not? Explain mathematically. Yeah. All right. So that's great and all. That's fun. That's kudos to be able to be given a graph and find out where it's discontinuous. Sure. But how do I find out where something is discontinuous in general? Like if I'm not given a graph, how do I know where it's continuous and where it's discontinuous? Because that is a very useful thing. Case in point, we can only bring the limit on the inside if we know that a function is continuous there. Like going way back, don't worry, I'm coming right back. But going back to unit 1.2, the 3 properties that we learned right here, there are 5, whatever. The composition rules. We could only bring the limit onto the inside provided that the function that we were bringing it onto the inside of was continuous at the value. So going to that, like going backwards for a second for 1.4, this one right here. I was only able to bring the limit onto the inside. This one's where it gets a little bit hand wavy, but the idea still stands. This function, x squared plus 2 in the denominator inside the square root, that function is continuous everywhere. The square root function is continuous for any positive real number. As long as it's a positive real number, the square root exists. So the fact is I can bring the limit onto the inside because the square root function is continuous for all numbers greater than or equal to 0. That is the reason for it. So that's why one of the big reasons why we would study continuity. The other thing, so you probably you might be wondering, and I would hope someone was wondering, the question is why? Why do we care about this at all? That is one mathematical purpose. In the grand scheme of things, not important, right? This is not going to save your life. If you are broke, if you are like dying in a car that's going into the water sinking, it's not like you're going to be able to recite the definition of a continuity and it's going to save your life. Unless I'm there, because I will wait until I hear that definition. I'll just be watching you like panic and like, nope, you got it. What's the third one? What's the third one? Come on, you're nearly there. But anyways, the big implications is that actually continuity is pretty much in the backwork of any theorem that requires functions. Almost all of them that you see in all of mathematics from now on, it's usually saying assume f is continuous, because without continuity, a lot of things start to break. So is it useful in the real world? No. Is it useful in all of the theorems that are required for the real world? Yes. The fundamental theorem of calculus requires the function to be continuous. A lot of upper division theorems in like differential equations and in multivariable calculus, they require your function to be continuous. Without that property, things kind of go out the window. So that is a reason why we like continuity. But back to the point, how do I find continuity of a given curve without being given its graph? As a small little pseudo definition, we say that it's continuous on an interval if it's continuous at each point inside the interval, and we say it's continuous everywhere if it's continuous on the whole real line. So from negative infinity to positive infinity. So the thing is, polynomials are continuous everywhere, and that makes sense. We learned about how to draw polynomials in Math 126, and they always end up looking something like that, right? The number of bumps and hills and valleys changes depending on the degree, but overall, they always end up looking something nice like that. Polynomials are continuous everywhere. And then the rest of them, all rational functions, radical functions or root functions, trigonometric functions, inverse trigonometric functions, exponential and logarithmic functions. That's basically encompassing everything that we usually encounter, besides piecewise functions, which we'll talk about there, a special case. They are all continuous on their domains. You guys remember how to find domains, though? It's been a while. It's been a while. But the domain, you're looking for all the places where your function would not exist. That's what you're looking for. So when it comes to a radical function, like the square root function, sorry, even radicals, when you're looking for the square root function, you're trying to make sure that the inside is greater than or equal to 0. If you're dealing with a function that has a denominator, you're trying to make sure that the denominator does not equal 0. If you're dealing with a logarithm, you need to make sure that the inside of the logarithm is strictly positive and all that stuff. So we've got several examples here. F of x equals negative 17 x to the 9th plus 6x to the 7th minus 2x cubed minus 90x plus 11. Where's that continuous? Everywhere. It's a polynomial. So polynomial. So that means the interval in which it's continuous is the whole real line. You can write Negative infinity to positive infinity. Some students, if they want to sound like a cool person, they'll write that bold-faced R. That's the mathematical way to say that. That's the lazy mathematician's way to write it, but either way is fine. Okay. I'm going to draw something in red because this is a big no-no. Student says, John Doe student, silly John Doe, getting into it again. It's like, oh, x minus 1 times 3x plus 2 over x plus 1 times x minus 1. Oh, I can cancel those. And yes, you can, but that, remember that I think we talked about this the first day. This becomes this, but you have to say provided x does not equal 1. There's that added caveat. When we cancel out a factor, we're claiming that these two things are equal, but we need to make sure we mention the caveat or we keep it in our minds because this does exist at 1. This does not. This becomes 0 over 0. So, and 0 over 0 is indeterminate. It doesn't exist until we know more. And even then, it doesn't really exist as a finite value. It's more of a limiting process. So the thing is, when it comes to looking at denominators, don't bother with the numerator. Even if it's a factor of both of them, that doesn't change anything when it comes to continuity. With limits, it does, right? When we were trying to find limits, but that's not what we're doing here. We're finding continuity. So, caution. Don't bother with the numerator. It doesn't cause domain issues. The numerator equaling 0 does not matter. The numerator equaling 0 does not change anything, right? 0 divided by 5 is 0. 0 divided by negative 3,000 is 0. It doesn't bother the function at large. The things that bother the function is when you divide by 0, because then you either get a number divided by 0, which is undefined, or you get 0 over 0, which is indeterminate. So when we're looking at this, we need to find its domain. That's done by setting the denominator equal to 0. So we need to make sure that x squared minus 1 does not equal 0. That means that x cannot equal 1 or negative 1. So reiterate that one more time. I don't want to bother with the numerator. It doesn't cause domain issues. The 0 in the numerator is not the issue. It's dividing by 0 in the denominator. That's an issue. We can't divide by 0. Whether it be 0 over 0 or number over 0, regardless of that fact, it always ends up causing problems. So we need to set the denominator equal to 0. We find, I mean, you can factor it if you'd like, or you can just see that it's going to be plus or minus 1 in this case. And so the answer, notice this asking me for the domain. It's asking me for the intervals on which it's continuous. So this function is discontinuous at 1 and negative 1. But that means that it's continuous everywhere else. So it's continuous on negative infinity, parenthesis, negative infinity to negative 1, and parenthesis, union, parenthesis, negative 1 to 1, and parenthesis, union, parenthesis, 1 to positive infinity, parenthesis. Hopefully you can see that by looking at what we need to pluck out. But if that's difficult for you, that's totally understandable. What you can do is you can draw a number line to kind of convince yourself of that fact. Here's the number line. Here is negative 1 and 1. We're plucking these two values out, but everything else is fair game. All the red is fair game. And that ends up being negative infinity to negative 1, union negative 1 to 1, union 1 to positive infinity, all with parentheses because they have to be excluded. All right. And any questions on that? The next one, and then I'll have you guys do D, and then we'll take our break. C we're going to do together because it's going to remind us of something we haven't done in a while. So So log base 3 of x squared minus 2x minus 8. Where is that continuous? You need to make sure that it's well defined, that you need to find its domain. And in order to do that, you need the inside of the logarithm. We need x squared minus 2x minus 8 to be strictly greater than 0. Not greater than or equal to. Not less than or equal, not less than, not equal to. Can't have it be equal to. So, do you guys remember what those are called? It's not linear, so it's non-linear inequalities. My favorite thing from 126. Way too fun to do. We got to factor it. So this is x plus 2 times x minus 4 is strictly greater than 0. That gives me the VIPs. X equals -2 and 4. If you don't remember this process, by the way, of solving a nonlinear inequality, I highly recommend going up and watching my videos on it. There, in the pre-calculus section, that's unit 2.6. It's called nonlinear inequalities, or you can just look that up online because this is the way I do nonlinear inequalities, but there are other methods that work just the same. I'm biased, but I think that my way is superior, but be your own person if you'd like to do it a different way. So if you're going to do it my way, you found your VIPs, your very important points. And I know they're not points, they're values, but Viv doesn't have the same ring to it. So deal with it. Here is -2. Here is 4. And we use some test values. X equals -3, x equals 0, and x equals 5. And the way I work through these ones, in case you did it differently, I use some test values. If you learn the multiplicity trick, you will get a kudos on the paper. I will look through trying to find the a kudos bar box. If you guys remember kudos bars, does anybody remember kudos bars? Oh man, they were marketed as like granola bars. They were just candy bars. They were delicious, but the early 90s were a time of ridiculousness in terms of foods for kids. It's healthy. It's got granola in it and M&Ms, everything the body needs. Everywhere. Anyways, so now that I've found the two values that kind of isolate the intervals, now I'm going to test a value inside each one. That's why I chose -3, 0, and 5. And now I plug in these values into the expression to determine the sign, to determine the overall sign. So -3, we're going to get a negative times a negative. That's a positive. That's a piece that I want. I want to be greater than 0. Plug in 0. I'm going to get a positive times a negative. That's a negative. That is a piece I don't want because I want my thing strictly positive. And then 5. That's a positive times a positive. That's a positive. And that's the piece that I do want. So that is my domain, which is also the intervals on which I'm continuous. So negative infinity up to -2, parenthesis, union 4 to positive infinity. Any questions on that?
Is natural log also just greater than, or is it greater than or equal?
All logarithms need to be strictly greater than 0. So I use log base 3, but you could just as easily ask the same question with natural log or log base 10 or log base 3/2, and it would still be the same process. All right. Any other questions on that? So we're looking for domain issues. All right. I'd like you guys to work on. Oh yes, Parker.
What was the point of doing
The sign chart.
Yeah.
So that was to determine where it was greater than 0. Because great question. So to recap what we did, because that was kind of an isolated step, we needed to in order to find the domain of this function, we need to know where the inside is strictly greater than 0. And that is found by doing a nonlinear inequality, by setting up a sign chart to figure out where it's positive and where it's negative. Once I found that, that is telling me where this function is defined, and that ends up being because of the theorem we just had above, that coincides with where it's continuous. The places where the function exists is the places where it's continuous for us. Once you get into like 400 level mathematics, you start talking about the weird cases where you really need to be asking where, like you get, for us, we're going to be dealing with, these are the functions we're going to be dealing with. We're going to be dealing with polynomials, roots, radical, trigonometric, inverse trig, and exponential logarithm. That's about it. We're not going to be dealing with these weird functions that you see in Math 400 level courses. That's for the math majors to do. Is that okay? And the last one. So I'd like you guys to work through it. Notice that there's two conditions. I'm going to slowly fill in details, but I want you to work through them yourselves. I have the answer up here if you'd like to check your work. And I heard these two talking up here about the bracket situation. The most correct answer is bracket -7/2 to 5 union 5 to positive infinity, with everything else being parentheses besides that bracket. But because it can be kind of weird talking about what happens at an endpoint, because the function that, like, we were talking about this when it came to that limit in 1.3 where we had the square root of 4 minus t squared, where like the full limit does technically exist, even though the left-hand limit didn't exist. So if you put parentheses -7/2, I would not mark you down. I would not, I would give you this, I would give you full credit there because that's a very ambiguous case. But technically speaking, it should be bracket -7/2 to 5. Now, I wanted to go, unless there's any questions about that, I'm going to go over it real quick. Thing is, we have two different conditions. We basically have a function that's comprised of two functions. The first function is only defined so long as the inside is greater than or equal to 0, meaning that we do need, in order for k to be defined at all, we need to have that x be greater than or equal to -7/2. Otherwise, if we try to take the square root of a negative number, and that would be a problem. So even if it does work in 7 over x minus 5, it wouldn't work in this, so it wouldn't work with the whole function. The other condition is that we can't be dividing by 0. So even though you can plug 5 into the radical portion and get the square root of 17, which is a number, it exists, that's not enough because you'd get the square root of 17 plus undefined, which doesn't make any sense. So we also need the fact that x cannot equal 5. So we have to take both of those into account. The red condition is that everything needs to be greater than or to the right of -7/2, but the 5 causes us to have to exit that piece out. And then that's where we get bracket -7/2 to 5 union 5 to positive infinity. Now, these are fun ones to do at some point else. I got them with a little bit of spiciness, a little bit of stank on it. We got K with the tilde. I forget what that means. I forget what that's called besides just a tilde. What doesn't matter. This one, square root of 2x plus 7 plus 7 over x plus 5. The only thing that's changed is that x minus 5 is now turned into an x plus 5. I'll give you the answer so you can verify it on your own time. You don't need to write these down. You can like write them off on scratch paper and prove them to yourself. This one is negative 7 halves to positive infinity. That is the answer. And this last one, the only thing that's changed, it's still 7 over x minus 5 like the first one. But instead of being a square root, it's a cubed root. This one, the answer is negative infinity to 5, parenthesis, union, parenthesis, 5 to positive infinity. So try those ones at home and verify it to yourself. If you get stumped on it, ask me on Wednesday and we can go over it. But then we're going to take our break and we're going to work on piecewise functions along with some really fun problems coming up after that. All right, let's take a break. Let's come back at 10:16. All right, so we're back. And now we're ready to talk about something else. So piecewise functions kind of fall into their own realm. They have their own unique situations because now we're taking, instead of just taking all the functions we know and love, like all of our exponential functions, logarithmic functions, and so on and so forth, now we're piecing them together. And as we saw with piecewise functions, they can have a lot of weird stuff happening. So they end up being things that we need to be more careful on. So here is the typical procedure to do this. So step one. Step one is to find discontinuities on each piece within its interval. Step one is to find the discontinuities of each piece within its domain restriction. So, in the example, we have two pieces. For y equals 10 over x plus 1 times x minus 2 on x is greater than or equal to 0. Where is that function discontinuous? So just looking at the top function, ignoring everything else. Like if let me grab a large color. If I just look at that, y equals 10 over x plus 1 times x minus 2. Where is that discontinuous? Negative 1 and 2. Yes. So if I'm just looking at that piece, that function, ignoring everything else, that thing is discontinuous at, so this is sorry, just give me a second. We'll explain. So discontinuous at x equals negative 1 and 2. However, x equals negative 1 is not in our designated piece because x is greater than or equal to 0. So only discontinuity is at x equals 2. Let's explain that. While you're writing that down, I'm going to draw something I'm going to draw what the curve looks like. So, -1. Okay. Okay. No, come back. Okay. So once again, yes, the actual curve, if you're looking at y equals 10 over x plus 1 times x minus 2, it is discontinuous at -1 and 2. However, we are on our function f, which is the function we're really concerned with, is where that thing is continuous. It is only equal to this curve for x values greater than or equal to 0. So -1 never becomes a problem because the curve isn't defined as this curve at -1. So the only discontinuity from this piece is at 2. And I'll give a picture representation in just a moment. Then for y equals x minus 5 on x is less than 0, is this function discontinuous anywhere? No, it's a polynomial. It's not a very exciting polynomial. It's a line, but a line is still a polynomial. And polynomials are defined everywhere. So no discontinuities. Because x minus 5 is a polynomial. No issues. There's not dividing by 0. There's no square roots of negative numbers. There's nothing like that. So that's not an issue. All right. So to look at it, to understand what's going on, why is it that I can just do this? This right here in purple, that is going to be the line y equals x minus 5. Not perfect, but it's just x minus 5. And the other graph right there in blue, that is y equals 10 over x plus 1 times x minus 2. That is that curve, roughly speaking. It's not perfect, but that's what it should look like. Now, yes, if you're looking at the entirety of this graph, yes, it has a problem at -1 and a problem at 2. However, our piecewise curve is only defined for values greater than 0. So this piece is gone, and this is gone. And that's all I have from that. And the other portion comes from this graph, which will end up being like this. Now here's the question. Okay. And I don't know exactly based on my head stuff, I'm not sure if they connect there, but that's what it's going to look like roughly. And that leads us to the second step. Does anybody have any questions about why -1 is no longer included in the discontinuities? So what was special about 0 is 0 is a dividing value. And as such, we have to worry about whether or not this is here, here, or up here, or something like that. Because if it's right here, then the point gets sealed up, and it will be continuous at 0. But if it was like this, then it wouldn't be continuous at 0. So not only do we need to check the each piece separately, but we also need to do the next step. Actually, I'm just going to make that really small just so that I can deal with it later if I want to talk about it. The step 2, which honestly could be done first. It's not a requirement to do it in this order, but this is the way I like to work through it, is to determine if discontinuous at dividing values. Determine if you're discontinuous at the dividing values. We've now already checked all the main portions. The only thing that's left is looking at the isolated situations where you have dividing values, because as we've seen with piecewise functions, sometimes they jump, sometimes they connect. And so we need to know. So in the example, the only dividing value is x equals 0. So for x equals 0. First things first, we need to check to make, so the 3 conditions of continuity. You need the function to exist there, you need the limit to exist there, and you need them to be equal. So, first and foremost, I'm going to check to make sure that f of 0 exists. Would I plug this into the, if I'm trying to find f of 0, would I plug it into the top or the bottom? The top, because the top one is greater than or equal to 0. So f of 0 would be 10 divided by 0 plus 1 times 0 minus 2. That's going to be -5. So f of 0, f of a exists. Cool. That is checked off our list. Do we need to, like, I know we probably could see that by ourselves and see that it works and not have to bother even checking it. But if you want to present a formal mathematical argument, you do need to show that it exists at that value. But that's not enough. Remember, continuity requires the limit, the function to exist and the limit to exist. Now, the problem is this is not going to be a nice limit to just immediately find because it's a dividing value. On one side of 0, it's one function, and on the other side, it's another function. So we need to use one-sided limits. Next, show limit as x approaches 0 of f of x exists. So the limit as x approaches 0 from the right of f of x . As a reminder, while you're writing that down, the reason why I'm doing this limit from the right and limit from the left is because our function is 2 different things, depending on whether you come from the left or come from the right. If you're approaching 0 from the right, you're talking about numbers that are slightly larger than 0 on the number line. So that would mean you're greater than 0. So this would become the limit as x approaches 0 of the top or bottom function. The top function. 10 over x plus 1 times x minus 2. Let's reiterate that just one more time, once you've written it down. So we're needing to check the one-sided limits because we don't actually have a consistent function at 0. We did that last time with the, like if you go back to 1.3, when we were talking about piecewise functions, at one point we asked for the limit as x approached like 1, and that was in the interval, so we could use a full limit. But at dividing values, the function's different on different sides of it. So if we're approaching 0 from the right, we're talking about numbers that are greater than 0. And so, looking at our piecewise function, it's defined as 10 over x plus 1 times x minus 2 if x is positive, it is greater than 0 or to the right of 0. And then we can plug it in and you'll end up getting 10 over 0 plus 1 times 0 minus 2, which equals -5. Yes, I know we already just did that computation, but sometimes redundancies have to be shown, right? We already evaluated that number, but it's two different contexts. Here it was evaluating a function. Here it was evaluating a limit. So yes, it's the same computation, and that's for good reason. That's a consequence of the fact that that function is pretty nice at zero. And not by pretty nice, it's very nice at zero. That's just by consequence, but it still needs to be done both steps because one of them you're talking about a function value, one of them you're talking about a limit value. Two different things, very closely related. Then we'll check the left-hand limit. The limit as x approaches 0 from the left of f of x. That'd be the limit as x approaches 0 from the left of x minus 5. Because if we're approaching 0 from the left, we're talking about numbers that are slightly less than 0. So to the left of the number line. And that would precisely happen if we were in piece 2. That's where piece 2 is defined for values less than 0. And that's a nice function. There's no issues plugging in 0, so we can just immediately drop the limit and plug it in. 0 minus 5 equals -5. We got samesies. And because we got samesies, that means that the full limit now exists. Now that we've checked that the left and the right hand limits did agree, they both exist and are the same number, hence samesies. I want to see that in the notes on your exams. I want to see samesies if it ever shows up. Kidding, you can just say same, whatever. But either way, the fact that the left and the right hand limits are equal to each other means that the full limit exists. That's a requirement. That's a theorem from 1.3. So the limit exists, the function exists. So I mean, it might even add that here real quick. So, quote unquote, the limit as x approaches a of f of x exists. And we get to put another green check mark. The full limit existed, the function existed, and the last thing to do is to show and the limit as x approaches 0 of f of x equals f of 0, which equaled -5. So f is continuous at x equals 0. So the limit existed at 0, the function existed at 0. So, and they were equal to each other. So all three conditions are satisfied. The function existed, the limit existed, and the limit and the function were equal. So it's continuous. So in fact, my drawing was not actually correct. This should actually be like that. And therefore, if you were to draw this curve, this point gets filled in. And so if you're drawing it, it's continuous here, still continuous, still continuous. Then at 2, we have an infinite discontinuity. We had or you could really think of it like a jump because we had to jump back up to here, and then like that. So that's what the curve actually ends up looking like. Do you need to have that known? No. If you know this procedure and why it works, that's all that really needs to be done. And so the last step, step 3, in the little space that we have left, is to combine steps 1 and 2 to get answer. That should all be in blue. So in the example, only discontinuity at x equals 2. So negative infinity to 2, parenthesis, union 2 to positive infinity is our answer. Sure, we'll use an oval this time. We're going to recap this process on the next one. Yes, GT.
So were we using the limits just because, like, for x minus 5, we knew that it had to be on the y axis somewhere, so we had to find the limits to see where it connects.
I'm sorry, say it one more time.
Like, when we did the limits, was that only to find, like, if the x minus 5 was equal to where, like, the
Where-
positive limit and the negative limit would be?
The left and the right hand limits? Yes, yes. We only did that one at 0 because that's a dividing value. Everywhere else, we don't really need to use limits because it's going to be a continuous function on each piece. Well, and not a continuous function, but it's going to be its isolated function where we only need to do, let me recap that in a different way. But yes, I'm going to answer your question. So to finalize this process, and then we'll, we maybe, let's see here. We've got this problem, and I want to get to the other two because the other two are more fun. So we'll do those ones, and then if we have to, we'll save this one for another time. But when it comes to a function, a piecewise function, on each piece, it is a function itself, right? For this this next one here, you've got a rational function, you've got a constant function, and you've got a quadratic function. And on each one of those pieces, we can analyze whether or not that function is continuous using this, this theorem right here. A function is continuous on its domain. All the functions that we'll be dealing with in this course, they are continuous on their domains. So looking at each one of these ones here, 2 is continuous everywhere. So I don't really have any domain issues with it. Negative x squared plus 26, that is also going to be defined everywhere because it is a polynomial. It's a quadratic polynomial, but a polynomial nonetheless. And so it is continuous everywhere. So it's especially continuous for values greater than or equal to negative 4. But this one here, 24 over x squared minus 2x minus 15, that could have discontinuities if you divide by 0. So once we've identified all the continuities on each piece, then we need to make sure whether or not they actually connect at the dividing values. As we saw, it could have been that the curve ends up looking like this, or it could be that this piece fills in the hole like that. So it's not enough to just check each piece individually. We also need to check the dividing values. So for this one, also please notice the difference in terminology between this example and the previous example. Previous example says determine the intervals of continuity. So that's where we're writing where it's continuous, whereas this one's saying find the x values at which it's discontinuous. So here we're not going to be finding continuity. So like we're doing the same thing. We're just answering a different version of the same thing. Does that make sense? So here we're asking for just the x values. And if we don't have time, I'm going to write the answers. It's going to be x equals negative 3 and 4. Looking at because we got 10 minutes. So we'll save these ones. Yeah, you know what? We'll do this one together, and then we'll save the other two. We'll savor them for tomorrow. We're just like we're saving those pieces of steak on our plate, like the two ones that they got no like none of that chunky like gristly fat stuff. It's just perfectly cooked. You know what I'm saying? You save those two pieces for last. All right. Okay, we'll get to that. So we will do this one first. So looking at each piece. So I'm going to break it down by step. Step 1. And once again, you can do step 1 first or step 2. That part of it doesn't really matter. It just makes sense to me to look at it holistically and then look at the finite, like the fine cases as well. But I've had plenty of students who do it the other way. They work with they work with the dividing values first, and then they move on to the each piece. So step 1. We got 3 different pieces. 4y equals 24 over x squared minus 2x minus 15, which equals 24. Let's see if we can factor it. On the quiz, by the way, that I just handed back, I still saw some problems with factoring. So please, 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 if you made some factoring mistakes, please take some time this week to practice your factoring. I don't care where you do it, how you do it. I've got videos on factoring practice. There's also videos online, or you can look up notes and stuff like that. You can look back over your 126 notes if you have them. Please look over your factoring skills if you had trouble factoring. It's not going away in this course. It's gonna be here forever. So please make sure you brush up on your factoring if you're still having some trouble. This thing factors to x, and then +3 and -5. So this thing is discontinuous at x equals. Oh wait, no, I'm sorry. I meant to write. Don't write that yet. I meant to write on to remind ourselves it's on x is less than -1. So it's discontinuous. That function without the domain restriction is discontinuous at -3 and +5. But one of those can be removed. Careful.
Oh,
5. It's not in our domain. -3 is. -3 is an x value that falls within our piece's distinction. For the top piece's distinction, it needs to be less than -1. So that is going to be a discontinuity. But since this is only defined as that curve for x values less than -1, 5 is not a problem. Then we'll do for y equals 2 on -1 less than or equal to x less than 4. No issues. Or let's say no discontinuities. Let's be particular. Y equals 2. Yes, go ahead.
sorry, that's just like labeling y coordinate that we're gonna have on the graph?
So I'm labeling it as a function. Y equals a function because each one of these pieces is a function itself. So like I'm saying this curve, y equals this curve on this interval.
Okay.
Is that okay?
Yeah.
Yeah, that's my notation of saying, because I don't want to write f of x because f of x isn't that curve only. It's all three pieces. So if I want to bypass that, I mean, another way you could write it is you could, some students will write, they'll write instead of y, they'll write f sub 1 or f sub top, f sub middle, f sub bottom. And that's another way to describe it. But I'm just trying to say that it's a function.
Okay.
Y equals 2, that is a constant line. It's a flat line. It's continuous everywhere. Another explanation as to why it's continuous everywhere is that it's a polynomial. 2 is a very, very simplistic polynomial, but it's a polynomial nonetheless. So it has no discontinuities. And last but not least, for y equals -x squared plus 26 on x greater than or equal to 4, also no discontinuities. So from the looking at each part holistically section, only one discontinuity has arisen, -3. The other pieces are continuous on everything, so they are continuous on their domain restrictions as well. That's step one, looking at the pieces. Now we're going to look at the places where the pieces connect and making sure they work out nicely. Thought I was tripping for a second. Step two, we've got two dividing values this time. We've got -1 and we've got 4. So we'll check each one, see what happens, and go from there. For x equals -1. F of -1 equals, which function do I plug it into? Top, middle, or bottom function? The middle function. That's where it's defined as -1 less than or equal to. So it's just going to equal 2. So f of a exists. Quote unquote, f of a exists. That's the first requirement of continuity. Second requirement is that the limit exists. So now we'll check out the limit. The limit as x approaches -1 from the left of f of x. Which curve would I be in? Top, middle, or bottom? Take a second. JT says the top, and he's correct. If we're approaching -1 from the left, we're talking about numbers slightly less than -1 because it's on the left of the number line. So that would be the top function. So this is the limit as x approaches -1 from the left of -24 over -1 squared minus 2 times -1. Oh, I'm sorry. -24 over x squared minus 2x minus 15. And then we can plug it in. -24 over -1 squared minus 2 times -1 minus 15. I don't know. I don't know why it's negative. Oh, did I not make the typo? Oh, okay, there should be a negative symbol there. I'm sorry. So add a negative sign on all of them. I'm sorry about that. So sorry. Apologies. So once again, it should, like the original function, it should have said -24. So on step 1, change it to y equals -24 over x squared minus 2x minus 15 equals -24 over x plus 3 times x minus 5. And then now it's going to be -24. And since -1 is not an issue, we just factored it and found out that -1 doesn't cause us to divide by 0. So we can just take the limit. And that will end up being 2. If you plug it into your calculator, right, you get -24 over -12, which is +2. Now, by the way, if you'd like to skip steps, you are more than welcome to go straight from here to writing the evaluation. I would like to see at least one step to show how the 2 came about. So whether, like, if you write this, like one of these 2 steps, either this step can be omitted or this step can be omitted. But one of them needs to be there so that I can see how 2 came to be. If you were a fellow student and someone was showing you this and they didn't have one of those pieces, you'd be probably confused at how it just becomes 2. Then we'll check the limit from the right-hand side. -1 from the right of f of x. In this case, it would be the limit as x approaches -1 from the right of 2. Because when you're approaching -1 from the right, you're talking about numbers that are slightly larger than -1, which puts us in the middle function. And the limit of a constant is just the constant itself. So these are equal. Which implies full limit exists. That is the limit as x approaches -1 of f of x is equal to 2. Yes, yeah.
Two, solely because of the dividing values for the top.
Yes.
Will there ever be a time where they're not equal, like?
When they're not equal to each other?
Yeah.
Excellent question. Let's check out x equals 4. See what happens. So now that we have the limit exists, the function exists. Oh, we're out of time. And they are equal to each other. It means that it is continuous at x equals -1. Then we'll go on to 4x equals 4. And for this one, we'll go ahead and compute that next time. You'll see that it does not exist. It's not continuous at 4. If you practice this tonight, you'll see that even though the function exists, f of 4 exists and equals 10, but the limit does not exist. And that means it's discontinuous at 4. We'll finish that off on Wednesday. So the quiz on Wednesday will have 1.4 on it and 1.5 up until this point, up until the previous thing.
What was it like?
So basically up until page 38, the whatever this one is about, example 1.5.3. That's where it will finish off. Okay, guys? That's where we'll finish. That's up. I'll update the homepage with that information in a little bit. But otherwise, have a great rest of your day. Happy studying. I'll see you guys on Wednesday. And then we'll see you then. Yes, next Monday is now the exam date.
I'll go.